Hello students, welcome to this module on chemical reactions. In this lesson we will learn about the 5 types of reactions, how to predict products, and have a go at some practice. I will try to be swift. Pause the video if you need to, or come back later and review. For this lesson you will need your periodic table and your ion formula chart. You will also need to know how we name chemical compounds, how we write their chemical formulas. You need to be familiar with ionic charges, how to use the periodic table, and chemical bonding. We have been preparing for this chapter for quite a while. All the things we've been studying this semester lead up to this chapter. A big part of chemistry is chemical reactions. Chemists have a shorthand system to convey the conversion of one set of substances into another. This is the chemical equation. Here's an example of one. Hydrogen and oxygen gas form water. The reactants, sometimes called reagents, appear on the left side of the equation. These are the starting materials. The products, the results of the reaction, these appear on the right side of the equation. Note the plus symbol between hydrogen and oxygen. This symbol is used to separate the individual substances. The arrow represents the chemical change. Don't forget hydrogen and oxygen are both diatomic. H2O, water of course. Subscripts represent the number of atoms of a particular element in that substance. The coefficients, those numbers appearing in front of the substances, these are used to balance the reaction. The law of conservation of mass states that no new matter is created nor destroyed, so we must finish with the same number of atoms that we started with. So the coefficients tell us how much of each reagent we start with, or how much of each of the products will form. Be sure to note the difference between a subscript and a coefficient. Again, the subscript indicates the number of atoms within a substance. The coefficient indicates how many particles of that substance. You can't balance a reaction by changing the subscript, only the coefficient. This table summarizes the symbols used in chemical equations. Again, the arrow denotes a chemical change, separates the reactants on the left from the products on the right. Some reactions can run forward and reverse, called reversible reactions, so a double arrow would be used for those. Plus symbol, again, separates individual substances. A triangle represents heat, usually written over the arrow. No reaction is abbreviated NR. The phase or physical state of a substance may be indicated. Solid, liquid, or gas. A down arrow or an up arrow could be used to represent solid and gas respectively. Aqueous, those substances dissolved in water, and oftentimes special conditions may be written over the arrow, such as the presence of a catalyst or the specific temperature the reaction is run. With the vast library of substances that can be interconverted at the chemical level, we will never run out of new reactions to study. In fact, the sheer number of possibilities might be overwhelming even to a highly trained chemist. So we have devised ways to categorize chemical reactions. This helps us better understand chemical reactions by making us reflect on their similarities and differences. There are many ways to classify chemical reactions, but the most general system consists of 5 simple types of chemical changes: synthesis, decomposition, single replacement, double replacement, and combustion. The first of these, synthesis, sometimes called combination, takes place when 2 or more smaller reagents combine to form a single larger product. The general equation here, A plus B produces AB. Synthesis reactions occur when 2 or more elements or compounds combine to form a larger, more complicated compound. An example of this reaction, one we've seen demonstrated in class in fact, is the burning of magnesium in air. Magnesium metal reacts with oxygen gas to produce magnesium oxide. A couple of other examples to consider. Carbon and oxygen combine to form carbon dioxide. Water and carbon dioxide react to form carbonic acid. It's easy to identify a synthesis reaction because the product is a single substance. The reactants, as we've seen in the examples, can either be 2 elements or 2 compounds or some combination thereof. When a group 1 metal or an alkali metal and a nonmetal react, the product is a binary ionic compound. For example, potassium reacts with chlorine to produce potassium chloride. When 2 nonmetals react in a combination reaction, more than one product is often possible. For example, when sulfur reacts with oxygen, the product can either be sulfur dioxide or sulfur trioxide. More than one product is also possible from the combination of a transition metal and a nonmetal. Recall some metals have a variable charge, so for example iron reacting with sulfur can produce iron 2 sulfide or iron 3 sulfide. The next type of reaction is decomposition. This is a process in which a larger starting material is broken down into several smaller products, the reverse of synthesis. These reactions occur when a single compound is broken up into the elements that formed it, or into simpler compounds. The general equation here, AB, produces A plus B. An example of this reaction, when heated, mercury 2 oxide breaks down into the elements mercury and oxygen. A couple of other examples. Iron 2 sulfide can decompose into the elements iron and sulfur. The compound calcium carbonate can break down into simpler compounds, calcium oxide and carbon dioxide. Decomposition can be thought of as the reverse of a synthesis reaction because it involves a single reactant and two or more products. The products can be any combination of elements and compounds. Often these reactions require energy to get started. A common everyday example of a decomposition reaction is the one that occurs in your vehicle airbag. Sodium azide decomposes to release nitrogen gas. An electrical signal triggers this reaction. The sodium azide decomposes and releases nitrogen gas, which inflates an airbag quite quickly, in fact, about 30 milliseconds. Other compounds are mixed in with the sodium azide pellets to react with the sodium and form less toxic compounds. The next reaction to consider is a single replacement. Single replacement can be thought of as a combination of a synthesis and a decomposition in which one reactant replaces a part of another compound. Single replacement reactions occur when a free element replaces another element in a compound, releasing the replaced element. Our general equation here, A plus BC produces AC plus B. In this case, A replaces B in the compound, forming AC, and B is liberated. An example of this reaction is potassium and water, forming aqueous potassium hydroxide and hydrogen gas. Other examples to consider, iron plus copper 2 sulfate produces copper and iron 2 sulfate. Iron replaces the copper in the copper compound. Zinc reacting with sulfuric acid, H2SO4, produces hydrogen gas and zinc sulfate. In this case, zinc metal replaces hydrogen because the metal cation would be most attracted to the sulfate anion. Single replacement or single displacement reactions are easy to identify because both reactants and products consist of an element and a compound. So for example, zinc reacts with the solution of copper 2 sulfate. Note the zinc replacing the copper in the compound, freeing up the copper and forming zinc nitrate. Another example, chlorine gas reacts with aqueous sodium bromide. In this case, the halogen chlorine replaces bromine in the compound, thus forming sodium chloride and bromine gas. Now, whether or not one metal will replace another metal from a compound depends upon the relative reactivities of those two metals. So here lists the activity series of metals, which ranks the metals from most reactive to least reactive. Potassium and sodium are the most reactive metals. Silver, gold, and platinum are the least reactive. Since more reactive metals can replace less active metals in solution, any reactive metal will replace any metal listed below it in this activity series. So for example, iron can displace copper from a copper compound in solution, but iron cannot displace zinc nor calcium. Just as a metal can replace a metal, a halogen can also replace another halogen from a compound. Recall from our chapter on the periodic table that for the halogens, reactivity decreases as you go down the family. So fluorine is the most reactive halogen. Iodine is the least reactive halogen. So bromine is more reactive than iodine. So the reaction between bromine and sodium iodide will occur. However, bromine is less reactive than chlorine, so the reaction between bromine and sodium chloride will not occur. The next type of reaction to consider is double replacement. These reactions occur when an element or an ion in one compound trades places with an element or ion in another compound, resulting in the formation of two new compounds. The general equation here, AB plus CD, produces AD plus CB. By convention, when writing ionic compounds, the cation is written first, so for this generic example, A and C are the cation, B and D are the anions. A specific example of this reaction is the reaction between aqueous solutions of potassium iodide and lead 2 nitrate. In this case, a solid is formed called a precipitate, lead 2 iodide, and an aqueous solution of potassium nitrate. A couple of other examples to consider: silver nitrate reacting with sodium chloride. Notice that the silver and the sodium essentially trade places, forming sodium nitrate and silver chloride. Copper 2 sulfate reacting with potassium chromate. Again, the two metals trade places, forming potassium sulfate and copper 2 chromate. Double replacement reactions are sometimes called metathesis reactions. Generally, these take place in an aqueous solution, and for these reactions to occur, one of the following must be true. One of the products must be insoluble or only slightly soluble in solution, the formation of a gas, or the production of a molecular compound such as water. Here is a table summarizing the solubility rules for ionic compounds. Here's another look at that same table. I don't expect you to memorize solubility rules, but with practice, you do start to notice some trends or patterns. For example, notice that all ammonium salts are soluble in water. For lithium, sodium, and potassium, all of those salts are soluble in water, with the exception of lithium phosphate. Notice too that all nitrate salts are soluble in water. All chloride salts are soluble in water, with the exception of silver chloride. Another example, a precipitate of barium carbonate is formed when aqueous solutions of barium chloride react with potassium carbonate. Barium carbonate is the precipitate or the insoluble solid formed in the solution. Another example, aqueous solutions of sodium nitrate and calcium chloride are mixed. You might predict calcium nitrate and sodium chloride are the products of this reaction. However, both of the products are in fact soluble in water, so this reaction will not occur. Looking back at our first example, aqueous solutions of lead-2 nitrate and potassium iodide are mixed. Oftentimes, double replacement reactions are written as a complete ionic equation. This shows all the dissolved ionic compounds as free ions. Any ion that appears on both sides of the equation is called a spectator ion. They do not participate in any of the chemistry. They stay dissolved as ions in water. The net ionic equation shows only those ions involved in the chemical reaction. Our last reaction to consider is combustion, the highly exothermic reaction of a substance with oxygen. The general equation here is a hydrocarbon reacting with oxygen, producing carbon dioxide and water. We've seen this reaction many times in the lab. Methane gas reacts with oxygen to produce carbon dioxide and water. Combustion can be identified as it always involves oxygen as a reactant. Typically, the other reactant is a hydrocarbon. Those are compounds that contain hydrogen and carbon. They give off a tremendous amount of energy in the form of heat and light. The complete combustion of a hydrocarbon produces carbon dioxide and water. However, if the supply of oxygen is limited, combustion will be incomplete, and elemental carbon and toxic carbon monoxide will be products. There are reactions between oxygen and some elements that are examples of combustion. Magnesium and sulfur burning in the presence of oxygen, the production of water. These reactions could be classified as synthesis. Soon you will be expected to predict the products of reactions, but understanding the general types of reactions will help you do this. So to review, synthesis is the production of a single product. Decomposition is the breakdown of a single reactant. Single replacement reactions involve an element and a compound both as a reactant and as a product. Don't forget to check the activity series to make sure these reactions occur. A double replacement reaction occurs between two ionic compounds. You will need to refer to your solubility chart to make sure that these reactions occur. And finally, combustion. Reactions with oxygen, typically with a hydrocarbon that produce carbon dioxide and water. Now let's take a look at some examples. H2O2, hydrogen peroxide. This is your only reactant. Manganese dioxide is indicated as a catalyst here. So what do you think? Decomposition? Now you might think hydrogen and oxygen are products of this reaction. Energy is the driving force of the reaction. The combination of elements usually produces a tremendous amount of energy, so you wouldn't expect hydrogen and oxygen to be the products of this reaction. Water and oxygen are the products. Your second example, barium reacting with HCl, hydrochloric acid. Now here we have an element reacting with a compound, so what do you think? Did you say single replacement? Barium will replace the hydrogen because it would be most attracted to the anion chloride in the compound, producing barium chloride and hydrogen gas. Our third example, lead-2 nitrate reacting with magnesium sulfate. What do you think? Double replacement. We got two compounds reacting here. Again, the metals are simply going to trade places, thus forming magnesium nitrate and lead 2 sulfate. If you're familiar with your charges of the metals, you should be able to write the chemical formulas accurately. Another example, calcium oxide reacting with water. What if I told you that a single ionic product was formed here? Well, that'd be synthesis. Did you guess calcium hydroxide? Sometimes these are a little tricky. Without additional information provided, it might be tough to guess what product is formed. Your last one, ethanol reacting with oxygen. That's combustion. Ethanol, a hydrocarbon, reacting with oxygen is going to produce carbon dioxide and water. Now take a look at the worksheet posted on the Google Classroom, predicting products. The key is also posted there, but I encourage you to try it for yourself first, then take a look at the key. If you have any questions, please don't hesitate to send me an email. Until next time, I'll see you in the lab.